Hello, everyone. This is Dr. Hira. So, now we are going to discuss nucleophilic substitution reactions. Previously, we have talked about the alkyl halides, and we are taking that understanding for discussion of nucleophilic substitution reaction. So, nucleophilic substitution reactions is basically the one of the major uh, type of organic reactions which are happening, and we can easily convert alkyl halide into the number of different functional groups. But before discussing that how these nucleophilic substitution reactions happen, there is a need that we do understand that what are the key terms which are involved, and we will discuss again and again in the discussion of nucleophilic substitution reactions. So the first thing is to establish that what are the nucleophilic substitution reactions are. So generally the substitution reactions are when the one of the atom or ions is replacing the other one. So this is just simply substitution reactions. So you can further check the different kinds of reactions from my previous lecture on the kinds types of reactions on my YouTube channel. So the nucleophilic substitution refers to any reaction in which an electron rich nucleophile, meaning nucleus loving nucleophile, replaces a leaving group. So it means, from the definition, a nucleophilic substitution reaction is when there is a leaving group which will leave the starting material by the attack of a nucleophile, which is a rich, electron rich, and it is from the Greek word, it taking that term, the nucleophile means the nucleus loving, that it is looking for a electron deficient center or the zone. So, nucleophile, another way, is a molecule or ion that donates a pair of electrons to another atom or ion to form a new covalent bond. It is also termed as a Lewis base because, according to the Lewis definition of a base, a species which is able to donate a pair of electrons is a Lewis base. So, a Lewis base is again rich in electron, and when it is rich in electron and it is behaving as a source of an electron pair, so this is termed as a nucleophile. So in this equation, if you just look at this one, this is a generic equation. And here I am trying to build your concept that how a nucleophile is attacking and what is happening with that alkyl halide or any of the compounds, right? So now this is a nucleophile, which is a electron rich species, and it is negatively charged if it is not counterbalanced with one of the positive side. Then there is the tetravalent carbon species, because more of our discussion is about the organic compounds, and we are taking that carbon, which are the tetravalent, and we are just highlighting the leaving group, the side which is basically, or the group or the atom which is basically attacked by the nucleophile, and that it has to kick off from the starting material. So the nucleophilic substitution is a type of reaction, and this is a leaving group. And what is happening that this leaving group will leave that compound, and the bond will be broken between the carbon and a leaving group through the heterolytic cleavage. And I have explained that also in the alkanes and the alkyl halides. Particularly, you can check the lectures in the radical chain mechanism. So, reactions of the alkanes, where I have told and I have explained the homolytic and heterolytic cleavage. So this bond breaking through the heterolytic cleavage is giving you the leaving group with a negative charge. And then this carbon is getting electropositive because this is becoming deficient in electron. So this is looking for and this is seeking for a partner which can contribute and which can donate a electron pair to it. So here is a nucleophile to help it. So nucleophile will attack to that carbon, which is the electrophilic, or you can say the carbocation. So then there is an attachment of the nucleophile. So this nucleophile has substituted this leaving group. So this is a nucleophilic substitution. And because it is termed as what is attacking species. So a nucleophile is attacking. So nucleophile has substituted its leaving group. So that is why this is termed as a nucleophilic substitution. Here, the other term is a leaving group. So group that is displaced in a substitution or that is lost in an elimination is the leaving group. We will talk about the elimination later. Right now, we are just focusing and limitizing our discussion on the substitution so we can just understand properly that what is a substitution reactions first. Then the electrophile, as you have seen in a previous example, that carbon, by breaking the bond with the carbon in a leaving group, that get electron deficient. So then it is getting the partial positive charge, right? Um, when it is in a neutral form, and when it is leaving that leaving group is leaving that static material, so it is making that carbon the positively charged. So it means a molecular ion that accept a pair of electron from another atom or molecule is in a reaction is a electrophile. So, according to the Lewis definition of an acid, this is termed as an acid too because it is able to accept an electrophile, right? Is It is basically electron pair accepting. So this carbon is now is the Lewis acid, and the nucleophile is a Lewis base. So here you can see when there is a hydroxyl group, this is attacking on a methyl chloride, so it is converting the alkyl halide into the methanol. So here, this is an example that how we can transform alkyl halide into the number of different functional groups. So this functional group changes is happening through the nucleophilic substitution reactions, and this has made um, much applications in the pharmaceutical, synthetic chemistry, and industrial chemistry, because this substitution is enabling us to making or generating the number of valuable products. Now, the leaving group can be a halide X or other electronegative group that can form a stable anion or other stable species. The weaker the base, the better the leaving group. If the base is stronger, it means it has a stronger basicity and it is a very strong nucleophile, right? So if the base is a weaker, the better is the leaving group. Now we'll go for the nucleophilic substitution in haloalkanes, because I have told you that we will take our alkyl halide understanding and discussion for proceeding with the substitution reaction, because this is more promising and it has a more common applications on the haloalkanes. So, nucleophilic substitution is one of the most important reactions of haloalkanes and can lead to a wide variety of new functional groups. Some of these reactions proceed smoothly at room temperature, others occur only at elevated temperature. So, there are some of the trends you have to keep in your mind that what the nucleophile can be, and you should take in your mind that what kind of different bond formations are happening in a nucleophilic substitution reactions. So, the very first case is this one. If the nucleophile is negatively charged, for example, OH negative or the alkyne anion, then, in a substitution reaction, the atom donating the pair of electrons become a neutral in the product. Okay, that makes sense. So here I can show you the example. So for example, there is a hydroxyl. This is negatively charged nucleophile, and when it is becoming the part of this one and it is substituting this leaving group, so at the end in a product, this negative charge has balanced with this one. So it is now the neutral species. Now, the second one is if the nucleophile is uncharged, as for example, ammonia and CH3OH, then in the substitution reaction, the atom donating the pair of electron becomes positively charged in the initial product, right? So, initial product needs to focus, because if you are want to write the ultimate product, so definitely that is going to the most stable neutral species, what are the most favorable charges on and the bonding of each atom. But otherwise, initial, the once the product or the intermediate product it is forming, unless there is another thing to capture that extra proton or um, to make it the neutral one, so then it will become the positively charged. So we can see some of the example in I will draw for you. So here the next thing is in the middle of the table are two reactions involving, I will show you the list of that one. That is the N triple bond C negative and HC triple bond C. So one is a nitrile, another one is the alkyne nucleophile. In these nucleophilic substitution reactions, the product have new carbon-carbon bonds. So here you can see that one. So what I was telling you is firstly, OH negative, this is negatively charged nucleophile, and when it is um, going through the substitution reaction, nucleophilic substitution reaction, so it is now becoming the neutral species. This is the alkoxy. There could be the methoxy, there could be the ethoxy, or any of this one. So one, you are treating that one. So this is becoming again the neutral one. And now we have developed an alkyl halide to an ether. So what the usual way to use the source of this alkoxy is the sodium ethoxide, sodium methoxide. So these we use for the reacting species as a nucleophile source, and then we can convert into the ether. Now the thiol, then of course it is becoming the part of it one. So as a whole, when this is a negatively charged in the starting of the reaction, so you will make a neutral species from that one. This is the alkyne cation and anion, and this is the nitrile anion, so nucleophile. And then again they are becoming the neutral species in the product one. Now, this is the iodide, one of another nice nucleophile. So then there is a methyl iodide as a product. Here, this is azide one, and that do exist as to counterbalance the charges because these are the highly elective and they are in a delocalization of the electrons. So this is the central nitrogen is getting the positive charge because now this is a quaternary because it is balancing this both of the nitrogen with the four bonding. So that's why this is becoming the deficient in electrons. So it is carrying the positive charge while the rest of the terminal nitrogens are getting negative. Now, when it is attacking on any of the alkyl halide, and here we are taking our example with the methyl bromide. So you can extend that change to the propyl, butyl, and you can just practice that when that what would be your product, right? So this is the methyl azide, and that is a product you will form. And again, because they are the number of the non-pair of electron, but otherwise this is the positive and this is negative, but overall the net charge is zero and this is a neutral one. Now we will see the examples when these are the neutral in the start and how they are converting into the positive charge species. So this is ammonia. So the initial product will be the CH3 and H3 positive because now nitrogen is again the quaternary as like this one, it is making the four bond. But eventually that will go for if you are adding any of the halogen or any of the you are making it with any of the base, so then it can collect that extra hydrogen from that one. So this is a CH3 and H3 positive, but eventually that could go to the CH3 and H2, the methyl amine, right? So next is the water molecule, and again that will be eventually go for the alcohol when there will be a species. So I can just write it. So to give you the idea that how that happen is if we are providing any of the OH, which is the negative, right, in a system. So that will abstract that extra proton, and again, then it will be the CH3OH, right? Now, this is the alcohol, and if you are treating the alcohol as a whole molecule to the starting material, which is the this alkyl halide, right? So this is converting into the ether, but at the moment there is this extra proton which has to be taken by any of the species which can abstract that hydrogen. So for this, we will provide any of that proton capturing species to the reaction system, so they can abstract from this one, and we will finally get the alcohol from this one. So the third point was that in all of these reaction, you can see that there is the carbon O, carbon S, carbon I, carbon nitrogen. These are the bonds which are developing, right? Carbon with any of the heteroatom. But in these two particular examples, right, here you can see that these are the bonds between the carbon carbon, right? So they are generating the bond between the carbon and carbon, because that methyl carbon, and then there was a carbonyl, there was a carbanion which is basically the nucleophilic site, and that is attacking one another carbon. So this is the bond between the carbon and the carbon, and the rest is the carbon and other heteroatom species, which are the nucleophilic atoms or the species which are making the bond. Now the next is another example I want to quote for you is, so this is the one of our alkyl halide, and we can name that one 1, 2, 3, and the 4, right? So this is the 1 bromo butane, and here we will see that how that react with the methoxide, sodium methoxide, right, in the presence of the methanol. So what will be our possible product? So here we are providing, whenever a molecule is written in a form of this negative and a positive, it means overall the molecule is a neutral. So this, we are using the sodium methoxide, but the nucleophilic site is this alkoxide, right? So you have to consult the, firstly you can take the help of that table I have just shared with you, that if you have the different nucleophiles, so what will be the class of the compound. But later you can see, you can practice and you will be able to form that what will be your possible product. So now we can see what is happening. So this methoxide ion is the nucleophile and bromide is the leaving group. So let me highlight for you again. So you have the proper understanding that which is the methoxide. So this is the methyl with the oxide. So this is a nucleophile from these the lone pair of electrons on oxygen, right? And the sodium is highly electropositive, so this will certainly take up with this Br, which is highly electronegative. So Br is a leaving group that is leaving that alkyl halide side and making this substitution with the methoxide. And here we have the 1-methoxy butane, or its common or trivial name is butyl methyl ether. So when you are writing the common name of the ethers, you always write the longer chain first as a YL, and the butyl methyl and ether, to show that what this is a class of the compound and this is the functionality. So otherwise the IUPAC name is, this is its IUPAC name. So 1-methoxy, and the longer chain was the 4-carbon chain. So this is the 1-methoxy butane and the sodium bromide as a product. Now, at the last, you have a task to complete and to submit on your LSM, the Moodle, and otherwise, the other students can just comment on the video, and I'll be able to answer you that either you are able to draw the right product, or you can just mention the name so we can check that one. And if you need a personalized um, evaluation, so you can contact me or you can email me. So here, these are the three reactions. You have to draw their product and you have to mention the class of the compound, right? So this is the alkyl halide, right? And this is a hexane, and there is a one chloro cyclohexane. And this is you are reacting it with the sodium acetate in the presence of the ethanol. Now, the next one is the iodo alkane, and this is the sodium sulfide. You are alkyl sodium sulfide, you are reacting it in the acetone, the solvent, and this is the alkyl halide, and you are reacting it with the lithium propine, right? So basically, in the chart, you can see that in some of the way, these were negatively charged written, right? Now, these are balanced with their counter positive side because as a chemical, as a compound, they do exist in a salt and a proper neutral molecules. And why I am writing the different solvents. So in a synthetic chemistry, we always have to select the proper solvent for the reaction system, that what you are getting in a product and what are your different reagents. Either you have to go for the aprotic or the protic solvents. So this is happening in an ethanol, this is happening in an acetone, and this is happening in a dimethyl sulfoxide. These are the three different organic solvents which we are conducting. So you just have to write the product which is forming by reacting these nucleophile with the alkyl halides. So that was for today. Have a good day. Thank you.